Good morning, students. Today topic is relation between linear and angular kinematics of a particle in circular motion. Relation between relation between relation between linear and angular kinematics angular kinematics of a particle of a particle in circular motion in circular motion. So here relation between linear and angular kinematics of a particle in circular motion. Here we have to consider a particle at P in the rigid body in the rigid body distance smaller from the axis through O point through O with the rotation of the body with the rotation of the body. This particle moves in a circle of radius smaller. This particle moves in a circle of radius r. So here we have to consider a particle at P in the rigid body, distance smaller from the axis through O point. To the rotation of the body, this particle moves in a circle of radius small r. So diagram. So this is the diagram. Here particle is P, distance R, and making angle theta in rotation. If in rotating through an angle theta, if in rotating through an angle theta, through an angle theta, the particle travels along the arc a distance s, a distance s. Then if in rotating through an angle theta, the particle travels along the arc a distance s, then theta is in radians, differentiating it with respect to here is equal to r into theta. So then theta is radians, differentiating it with respect to time. Differentiating it with respect to time. So ds by dt equal to small r into d theta by dt. Here small r is constant. Small r is constant. So we can write the above equation as ds by dt equal to omega r. But left hand side represent linear speed v, and therefore v equal to, we can write r omega. So this is the equation 1. Here what we are writing, if in rotating through an angle theta, the particle travels along the arc a distance s, then theta is in radians, is equal to r into theta. So differentiate it with respect to time, then we get ds by dt equal to r into d theta by dt. Here r is constant. And ds by dt equal to omega into r, v equal to r omega. So here giving a relation between the magnitudes of the linear velocity, and angular velocity. So differentiating equation 1 with respect to time, we get dv by dt equal to r into d omega by dt. So here a suffix t equal to acceleration r into alpha. So d omega by dt alpha. Here a suffix t is the tangential component of the acceleration of the particle, and alpha is the magnitude of the angular acceleration of the body. Where A suffix t is tangential component of the acceleration of the particle. Acceleration of the particle. And alpha is the magnitude of the angular acceleration of the body. Angular acceleration of the body. And the force directed towards or away the center of force is always radial and is represented by mv square by r. From this expression of force, we find that radial component of acceleration is v square by r. Radial component of acceleration is v square by r. So that is a suffix r equal to v square by r. From this equation, omega square r. The next topic is kinetic energy of a rotating body. Kinetic energy of a rotating body. Kinetic energy of a rotating body. So here suppose rigid body is rotating about an axis fixed in an internal frame of reference. Here omega be the angular velocity and a particle of mass m1 and distance consider r1.